Hey everyone, Norman here with the McWane Science Center, back again with another SciSpark. Did you know I'm actually a mathematician? I know, everyone hates math. I've heard it all before, but please, just let me show you how you can find the beauty of math everywhere, even in a bubble. Okay, so first off, I highly recommend that you check out my SciSpark on the beauty in a bubble to learn more about what bubbles are and how they work. But to summarize, a bubble is formed thanks to the unique surface tension in soap film, which is strong thanks to water, but not too strong thanks to the soap. Surface tension, the force of the water molecules pulling themselves toward each other, is why the soap film makes the shapes you see. This tension can be altered by outside forces, but the soap film will always tend toward the same goal: to use the minimal amount of film to hold whatever shape it needs to. This is the behavior of a minimal surface, something we mathematicians love to study. Don't let the fancy phrasing confuse you. A minimal surface is just what happens when something wants to cover as much as it can with as little as possible. For soap film, the outside forces cause the molecules to be forced in one direction, but then the surface tension pulls it back into its most compact and minimal shape. In a bubble wand, the soap film produces tension in response to being pulled on by the edges, making a thin sheet that fits the shape of the wand. In a soap bubble, that surface tension is produced in response to the pressure of the air inside pushing out. And the best shape to contain that air with the least amount of film is a sphere. Smaller bubbles have a greater surface tension, so they squeeze the air inside with greater pressure than a larger bubble. This means that smaller bubbles are more likely to pop than larger bubbles, something you may have noticed. The higher pressure in smaller bubbles is noticeable when you get a small bubble to stick to a large bubble, and you see the smaller bubble bulges into the larger one just a little bit. Two equal-sized bubbles have more of a flat boundary when combined. When multiple soap films touch, they pull on each other with surface tension as well, trying to minimize how much space they take up. This is why the bubbles merge the way they do, and why soap film bends the way it does on different wand shapes. And finally, with really weird wand shapes, like these 3D geometric wands, we can explore some insane soap film surface tension in action as the films minimize their surfaces in a battle between air pressure and tension from so many directions. All right, now that I've made a soapy mess everywhere, I think that's as good a place as any to end today's SciSpark. If you liked what you saw, be sure to leave a like and subscribe to the channel for more content. Until next time.